Hi guys. Today we're going to continue our lesson on solving inequalities algebraically, okay? And we're also going to be learning how to graph the solution set on a number line, as well as learn how to write the solution set in another notation called interval notation. Previously, we learned about set builder notation and roster notation. Today we're going to learn about another notation called interval notation, which involves a bracket system. So let's talk about interval notation for a couple minutes, all right? Interval notation is a notation for writing a solution set when the solution set involves a specific interval, okay? And we use either a soft bracket or a hard bracket to indicate whether or not the endpoints of the interval are included in the solution set or not included in the solution set, okay? So we may have an interval where neither endpoints are part of the solution set, where both of the endpoints are part of the solution set, or with one number as being part of the solution set. Depending on how it pans out, we might call that a bounded interval, right? A bounded interval which has two well-defined endpoint values versus an unbounded interval which has one or no well-defined input values. And what we're talking about as well-defined input values is actually a numerical endpoint, right? The other endpoint you might see might be infinity or negative infinity. And using infinity or negative infinity implies that we have these unbounded intervals which go on in either direction. So let's take a look at some bounded intervals, what that might look like. Okay, let's consider the inequality a is less than or equal to x, which is less than or equal to b, right? In this case, we could read that as x is between and including a and b. Because we have the less than or equal to part, right? The equal to part of the inequality symbol implies that that number is part of the solution set. And in this case, both A and B are part of the solution set. So the way we would write that in interval notation is with hard brackets. We would have a hard bracket A, that's the left boundary of the interval. Then we put a comma, and then we put the right boundary of the interval, which is B, with another hard bracket to indicate that B is also included. Maybe you remember from Algebra 1 where you used an open and closed circle system. So you may have had an open circle at a given value and then you shaded off into a direction, right? Well, open circles said that that number was not part of the solution set. But instead of writing open circles now, we're going to use soft brackets versus like a closed circle. When you had a closed circle, right? That meant it was part of the solution set. This time we're going to use hard brackets to indicate that it is part of the solution set. So whereas before we used open and closed circles, now we're going to use brackets, soft or hard brackets, on our number line. Just remember that if a number is not included, you're going to use soft. If the number is included, you're going to use hard brackets. And infinity as being part of an unbounded interval, infinity will always get a soft bracket. Whether it's positive infinity or negative infinity, infinity always gets a soft bracket. Let's see if we can write some inequalities in interval notation, right? So if we were going to graph the solution y is greater than or equal to 2 on the number line, we would have the number line with 2. Since 2 is included, we're going to use a hard bracket. And since it's greater than 2, we're going to be shading off to the right. So we're going to use a hard bracket at 2. And we're going to, and I'll do this, I'll shade off to the right, kind of like that. Okay? So that's what it looks like on the number line. In set builder notation, and this is what we talked about last time, we had something that looks like this. The set of, and this time it's y, such that y is an element of the real numbers, and y is greater than or equal to 2. This is set builder notation. It looks kind of like this. Now, we can shortcut that and we can write that in interval notation, right? So interval notation, we use the boundaries of our interval. So the left boundary of our interval is 2, and because this is shaded off to the right and never ends, the right boundary of our interval is positive infinity. Because 2 is included, it gets a hard bracket. Infinity always gets a soft bracket. Interval notation looks something like this. And we would read this as hard bracket 2, comma, infinity, soft bracket. Let's try another one. This time we have a compound inequality. Graph -2 is less than x, which is less than or equal to 1 on the number line. Basically, that's saying that x is between -2 and 1, but does not include -2. Notice it doesn't have the equal to part on the -2 part. So we're going to put -2 and 1 on the number line, and we need to determine whether or not we have soft brackets or hard brackets. And if you look closely, the -2 is going to have a soft bracket, but the 1 is going to have a hard bracket. And from here, we're going to shade in between. Shade in between. Now, what does that look like in set builder notation? Well, it's the set of x's such that x is an element of the real numbers, and x is between -2 and 1, but not including -2. In interval notation, that's much simpler. It's a soft bracket at -2, comma, 1, hard bracket. Now, solving inequalities is just like solving equations, right? We still use the properties of addition, subtraction, multiplication, and division for solving an inequality. However, there is one thing to keep in mind. So let's check something out. Let's say we have the inequality statement 4 is less than 7. If I apply the multiplication principle to both sides, I can say 4 times 2. If I multiply the same thing on both sides, 4 times 2 is less than 7 times 2. Is 8 less than 14? It is. But if I suddenly use my multiplication property on both sides and I make the multiplication part negative, so 4 times -2 is less than 7 times -2, then I have a statement like -8 is less than -14. Which is not true, right? This is false. So in order to make this statement true, in order to modify it to make it true, all we need to do is adjust the inequality symbol. We switch it around, right? We switch the inequality symbol around. And then we make a statement. This is going to be true for anytime you're multiplying or dividing by a negative number. What would we need to do to the sign in order to make this inequality true? Well, we would need to switch it around, right? Which brings us to the multiplication principle. Anytime you are solving an inequality and you have to multiply or divide, and you multiply or divide by a negative number, you must switch the inequality symbol around. All right, in order to maintain that true statement, anytime you multiply or divide by a negative number, you need to switch that inequality symbol around. Okay? So let's take a look at a few examples here. I've got a couple of them on here. Remember, we're employing the same exact properties of algebra that we did when we were solving equations with just that one little extra piece. Anytime we multiply or divide by a negative number, we have to switch the inequality symbol around. So what I did here was I solved the inequality, found the solution set, and then I wrote the solution set in interval notation. Notice the interval notation for these three examples. I'm going to encourage you to pause the video just for a minute and look through the three examples and see if you can see how we got the interval notation. Moving on to word problems, right? So this is a situation where we need to translate words into inequality symbols. And I put some of the most commonly used words which indicate that we're talking about an inequality. Words like is at least, is at most, is between, cannot exceed, maximum, no more than, no less than. And what we're going to do is we're going to translate these sentences into an inequality using a variable. For example, Sam walks at least 1.5 miles per day. What that means is that Sam's miles have to be greater than or equal to 1.5, right? If he walks at least 1.5 miles, 1.5 is the smallest amount that he walks. Is at most is just the opposite. At most, 5 students dropped the course. So the students has to be less than or equal to 5. Is between. The film is between 90 and 100 minutes long. So the minutes are between 90, and this would be a compound inequality. Minutes is between 90 and 100. Notice my less than, right? When you're writing a compound inequality about something in between, you're going to use the less than symbols. Interestingly, though, notice it says is between 90 and 100, but it doesn't say that it includes 90 and 100. If it did include 90 and 100, we would see the word inclusive in there. All right, inclusive indicates that those numbers are included. Cannot exceed. The cost cannot exceed $400. So the cost has to be less than or equal to $400. The maximum penalty is $250. So the penalty has to be less than or equal to $250. Noah consumes no more than 1,500 calories per day. So the number of calories has to be less than or equal to 1,500. Eric scores no less than 5 goals per game. So his goals must be greater than or equal to 5. These are commonly used phrases that can translate into inequalities. I put a couple word problems in here. Okay, I'm going to caution you to read these carefully. You'll notice we're using some kind of function notation here, right? You can work through this example here and see exactly what's going on, as well as example number 2. I'm going to stop talking, and I'd like you to look at example number 2 a little bit closer. And I want you to pay close attention to how we algebraically represented the part of the equation that's plus a commission of 5% of sales in excess of $10,000. Okay? So I want you to look at the equation we set up, which is, well, we set up 2 of them, right here and right here, how we algebraically represented 5% of sales in excess of $10,000. And then you'll see that how we solved it. So solving inequalities is just like solving equations, all right? Except for remembering that one little thing about the multiplication property. Anytime you're solving an inequality and you must divide or multiply it by a negative number, you must switch the inequality symbol around. We also learned how to write solution sets in interval notation using a soft bracket and hard bracket system. Again, I'm going to urge you to read the word problems carefully and just look them over. And then if you'd like to see the rest of these notes, like what the solutions actually mean, you can check them out on Schoology under the notes key. Otherwise, if you have any questions, please don't hesitate to ask me, and hopefully your practice will solidify your understanding of this concept.